Hello everyone, I'm Mian Tian. Today I will present the paper Why Language Models Hallucinate. This paper is published by researchers from OpenAI and Georgia Tech, and it is released in arXiv on September 4th, 2025. And in this presentation, I will cover these aspects: the introduction, pre-training errors, post-training and hallucination, discussion and limitations, and conclusions. And first is the introduction. What is hallucination? Large language models are known to produce overconfident, plausible falsehood, which diminish their utility and trustworthy. This error mode is known as hallucination. And take this prompt as an example. If we ask the language model, what is Adam's birthday? If you know, just respond the date and the month. And on 3 separate attempts, a state-of-the-art open-source language model, which is DeepSeek v3, output 3 incorrect date. Even though a response was requested only if known, the correct date is in autumn. And here I provide an example of more elaborate hallucinations. So here we prompt the language model with the sentence, what was the title of Adam's desertion? And the correct answer shall be in the 2001. However, none of these three popular language models, the GPT-4o, the DeepSeek, and Llama generate the correct title or year. And given that the hallucination is widely presented in the current state-of-the-art open source and closed source language models, what will this paper investigate? In this paper, they raise two arguments. First is the origin of hallucination after pre-training. The language models hallucinate because of statistical pressure during pre-training. And the second argument is the persistence of hallucination after post-training. The hallucination persists because of misaligned insensitive during evaluation. And for the first argument, they have 3 points. The first point is that the paper reduces the generative errors to a binary classification problem, which is the is it valid problem, or in short, IIV problem. And if facts are hard to distinguish from non-facts, a well-trained model will naturally produce errors. And third is this is not a flaw, but an expected outcome of density estimation on hard-to-learn data. And for the second argument, we still have 3 points. The first point is that the most benchmarks uses dichotomous or the right or wrong grading, and this rewarding guessing and penalizes admitting uncertainty, like saying I don't know. And the models are optimized to be good test taker, which reinforce hallucinatory behavior. And I will first walk you through the pre-training errors. So first, what is pre-training? The pre-training produces a base model, the head P, that approximates the true distribution of text P from a large corpus. This is a classic density estimation problem. And the core idea is that the paper shows that even with perfect error-free training data, a well-trained base model will still generate errors. And their analysis demonstrates that first, they observe that generating valid output is fundamentally harder than classifying if an output is valid. This is intuitive. And given the first point, we can have that this allows us to reducing the generative errors to a binary classification problems where the error sources are well understood. And following that, the analysis is general and applies to any density estimation task, not just the next word prediction. And yeah, and first, we need to introduce the definition of the general errors or the hallucination rate, the ERR, the ERR or the error. the base model here, the het P, is the language model produced by pre-training, viewed as a probabilistic distribution over a corpus of plausible string X. And each individual string X, small x in the corpus is an example. And the big X is divided into two categories, the valid example V and which are correct or factual strings, and errors E, which are the plausible but false strings, like hallucinations. And the key matrix defined here is the generative error rate, the ERR. And it represents the probability that a string sampled from the model's on distribution P hat will be an error. Or in other words, it is the total probability mass that the model assigns to all the incorrect strings in the set E. And this measures how frequently the model is expected to generate a hallucination. Finally, in this paper, they also assume a noiseless training distribution, Px. This is the idealized true distribution of the training data. They assume that the PE equals to 0, which means that the training data is perfectly factual and contains no errors. This simplification is because it allows the paper to show that hallucinations arise from the learning process itself, even when the source data contains no error. And this slides introduce the central idea of the paper's analysis, reducing the problem of generative error hallucination to a more familiar binary classification problem. The new problem is called the is it valid or the IIV problem. The intuition is that generating a correct response is harder than simply classifying a given response as correct or incorrect. To generate something, a model must implicitly walk through all the possibilities and decide which one is valid. And the IIV problem is a standard supervised learning task. We can imagine a data set where every possible string is labeled as either valid with the plus sign or an arrow with the negative sign, as shown in the left part of this figure. And the goal is to train a classifier to distinguish between them. And we can see from the right side of the figure, it illustrates why a classifier might fail, which in turn explains why a language model might hallucinate. The top panel shows an easy case like spelling, where valid and invalid examples are clearly separable. A good model can learn this boundary perfectly. The middle panel shows a poor model problem where the classifier is too simple to capture the true, more complex boundary. The true boundary is the circle, while the classifier is a straight line. And this leads to misclassification. And the bottom panel illustrates the arbitrary effects problem. Here, the valid examples are scattered randomly with no pattern. In effect, if a fact is not in the training data, it is statistically impossible for any model to learn it, making errors inevitable. By connecting generation to this classification tasks, the paper can use the well-understood classification error to explain this origin of hallucination. So with the previous two definition, we can formalize our research problem into this sentence. Can we establish a mathematical relationship between generative errors, such as hallucinations, and the IIV misclassification rate? Or in mathematical formulation, can we find the relationship between the left part in the bracket to the right part in the bracket? And to do this, we need to first formally define the IIV misclassification rate. So this slide shows, so here, the target function f is the ground truth that the classifier aims to learn. and it simply label any valid string from the set V as positive and any arrow string from the set E as negative. And this distribution defines the dataset for this classification task. It is constructed to be a balanced 50 by 50 mix of samples from the true valid data distribution and the uniformly sampled arrow in E. And uh, another critical step is that how can we turn the generator model, the p hat, into the classification model, the f hat? The classifier f hat in the equation 2, we can see that it makes its decision by looking at the probability that the base model p hat is assigns to a assigns to a given string x. If the model thinks that the string is likely, which means it assigns it a probability greater than a threshold, the 1 over the number of set E, the classifier label it as positive, and otherwise it is labeled negative. And finally, the overall misclassification rate, the error IIV, is defined as the probability that the classifier f hat disagree with the true label f on an example drawn from the test distribution. And this matrix quantify how well the base model's own probability estimate can be used to distinguish string from arrows. And here I will introduce one conclusion that is directly derived from the derivation in this paper. This is the first corollary. And first, we have defined the arrow IIV and the V set and the E set, and I will explain the delta function first. So let's first look at the definition of set A. A is a set of all strings that the model consider likely. It means that it assigns them a probability higher than the threshold of 1 over the number of set E. And the absolute difference in the definition of the delta function measures the discrepancy between the model's belief about the likelihood of set A and the true likelihood of that set. And in a sense, the delta is a measure of miscalibration. It quantifies how much the model's own probability estimates for likelihood outputs diverge from the actual probabilities found in the true data distribution. A small delta indicates that the model is well calibrated for this set of output. And the paper argues that the standard training objective naturally leads to model with a small delta. So why? And in this slide, I will briefly prove why a well-calibrated model will derive a smaller delta. So we consider the standard training cross-entropy objective, which is defined in the L loss function, and we introduce a hypothetic new probability distribution, the p hat s, which is created by taking the original model's distribution p hat and rescaling it. Specifically, it multiplies the probability of all the likely outputs, those in set A where the p hat is greater than 1 over the number of set E by a factor of s. And this new distribution is then renormalized to ensure its probability sum to 1. And the original model p hat is equivalent to this new model when the s equals to 1. And in this paper, they prove that the calibration error delta is equal to the absolute value of the derivative of the training loss L with respect to the scaling factor S evaluated at the point where the S equals to 1. This may be a little bit hard to understand. So how can we interpret this equation? So first, let's imagine that if the derivative is not 0, means that the delta does not equal to 0. And it means that the loss function has a non-zero derivative. And this implies that we could decrease the loss by moving the S slightly away from 1 by rescaling the probability. And uh, this means that the original model p hat was not at the local minimum. And on the other hand, for any class of language model powerful enough to approximate such simple rescaling, which means they are at local minimum, it means that the local optimization should yield very small delta. And from the previous colony 1, and they can derive some conclusions. The first is the hallucinations are inevitable only for base model. So first, the arrow lower bound of colony 1 implies that the language model which do not error must not be calibrated, which means that their delta must be large. And we can also prove it. If we consider a hypothetical language model that does not error, means its generative error rate ERR is 0. And then we put this ERR into the equation we introduced before, and we can derive this inequality. And we rearrange the inequality to solve the calibration error delta, and we can get the delta is greater than 2 times the IIV error minus the V over E ratio. And what can we get from this this derivation? First, for many real-world tasks like knowing arbitrary facts, the classification error at the IIV error will be significantly greater than 0 because the problem is inherently hard. And second, the ratio of valid to invalid examples is typically very small. So given that the first term of this equation is large and the second term of this equation is small, we can get these conclusions. The language model which do not error must not be calibrated. And this is contrary to the goal of pre-training. And now, in the previous slide, we only considered the scenario that is without prompt. And now that we are considered the scenario that with prompt. And if we just look at this equation, we can see that it's barely the same as the previous one, except we replace the VC and the EC with the max VC and the minimum EC. So I will explain these two terms first. So the term max CVC represents the maximum number of valid response for any single prompt. For example, if some questions can have multiple correct answers, this term captures the largest number of such answers. And the term minimum C, the EC, represents the minimum number of erroneous responses for any single prompt. And this ratio, this ratio VC over EC is typically small. For instance, I give an example here. In the arbitrary facts model we discussed before, a prompt about a birthday has only two valid response, which is the correct date and I don't know. So the number of VC is 2. And the number of erroneous response is 364, which is the other days of the year. So the EC will be 364. So the ratio between them is very small. And next, I will go through how to prove this main theorem, which is this inequality. So first, we will define two. First, we'll define two new constants, the small k and the big K, which represent the maximum number of valid response and the minimum number of the error response for any prompt. And also, this is just definition. And in the next step, we make two other definitions. First, the set A and the set B. The set A contains the response that the model thinks are likely because it assigns them a probability that is above the threshold of 1 over the big K. And the set B contains unlikely response with probability at or below the threshold. So also this also only definitions. And next, by definition, we can get the equation of the arrow and the arrow IV. The generation arrow, the ERR, the generation arrow is the sum of the probability uh, sorry, the generative arrow is the sum of the probability that the model assigns to errors it considers likely and errors it considers unlikely. And the classification arrow, the IV arrow, is the sum of the false positive and the false negative. And also this is by definition. And the proof proceeds in two steps. First, consider the above threshold part, which is the first term in the first equation and the first term in the second equation. And by for any errors in the first term of the first equation, its contribution to the arrow is the distribution of prompt mu c times the p hat, and by the relationship between the p hat with the big K, we can get that the mu times the p hat is greater than the mu over the big K. And also its contribution to the arrow IIV can be defined in a similar way, which we defined before, such that we can derive that the first term in the first equation and the first term in the second equation has such relationship that the p hat is greater or equal to 2 times the d. And for the below threshold, we want to show this relationship. And we derive this by construct this equation, and we replace the 2D by P, which is the definition of the D, and then we divide the P hat B with E into the P hat B minus the P hat B with V. And then we use the definition of the delta function, which is the distribution of the true the true distribution minus the model's distribution, and we substitute it into this equation, and we can get the this inequality. And then we, by definition, that the p hat is smaller or equal to 1 over big K. And we rescale this function by multiply the small k and then substitute it into the equation. And then we can get this inequality. And by combining the first inequality and the second equality, we can complete the proof. Yes. And by deriving this theorem, this paper can derive the relationship between the generation error with the binary classification error, and then we can use the series in the binary classification to analyze the generation error. So there are many error factors that could affect the base model, including the statistical complexity, as in the birthday, or arbitrary effect hallucination, or the pool models, as in the letter counting, or other factors like the GIGO, which in short is the garbage in, garbage out, which means that if you have like untrue, if you have errors in your training data, it will be duplicated in your base model. And then we will discuss each of these factors in the following slides. So the first is the arbitrary effect. The arbitrary effect. This slide introduced a stylish model called the arbitrary effect to analyze the hallucinations caused by the uncertainty, where the knowledge is simply absent from the data, and the model captures the situation like knowing birthdays, and where there is no learnable pattern. For each prompt, there is one correct answer chosen at random, and the only valid response are the correct answer or I don't know. All other answers are errors. And this paper also defined the singleton rate, which is the fraction of training examples that appears exactly once. The intuition is that these unique, rarely seen facts are a good indicator of the unseen portion of the data distribution. If a fact appears only once, it is at the edge of the model's knowledge, and the model is likely to err on similar facts it has never seen. And also the paper proves that the theorem 2, which provide a concrete quantitative link between the singleton, the SR, and the hallucination rate, the error. The first inequality gives a lower bound of the generation error. It states that for any pre-training algorithm, the hallucination rate is at least the singleton rate, which is the error is greater or equals to the SR. And minus a few small fractions. And for well-calibrated model where the delta is small, this means that if 20% of the facts in your training data appear only once, you should expect the model to hallucinate on at least 20% of similar facts. And the second inequality shows that this boundary is tight. It states that there exists an efficient algorithm that can achieve a hallucination rate that is very close to the singleton rate. This algorithm essentially memorizes facts it has seen and guesses randomly for facts it hasn't. Together, these bounds show that the singleton rate is not just a lower bound, but a very good predictor of the hallucination rate for arbitrary facts This strengthens the argument that such hallucinations are an inevitable statistical consequence of pre-training on data with a long tail or real facts. And for the second point, the poor models, this, this slide explains that the hallucination can arise from poor model, which means that the model's architecture is too simple to capture the true pattern in the data. And the concept of agnostic learning is introduced to formalize this. It defines the OPT G as the best possible error rate for any classifier within a specific family of model G. And if the optimal error rate is high, it means that no model in that family can do a good job. And this slide then connects this to the generative error by showing that the generative error the generative error rate is lower bounded by this optimal disclassification error. And the pure multiple choice here provided a tighter bound for scenarios like multiple choice questions, showing a direct relation between the inability to classify correctly and the inevitable of generating errors. Still, I put an example here. So this slide provides an example of the poor model problem using a classic trigram models. The trigram model here means that it predicts the next word based only on the two preceding words. In this example, the last two words of both prompt is out of. Both because the trigram model has such a short context window, it cannot see the crucial difference between she and he at the beginning of the sentence. Therefore, it cannot learn to correctly associate her mind with the first prompt and his mind with the second. And this corollary shows that for this simple task, any trigram model is guaranteed to have an error of at least 50%. We can simply derive this by put this c equals to 2 into the previous equation. And this illustrates how architectural limitations directly leads to unavoidable generative errors. And there are also other additional factors like the computational hardness, which refer to the fact that the AI system, like any algorithm, will fail to will fail on problems that are computationally interactable, such as breaking a secure encryption. And also another factor is distribution shift. For example, there are some the input may be not in the distribution of the training data. For example, the trick question like what is heavier, a pound of feather or a pound of lead? And the third factor is the garbage in, garbage out factor. It acknowledges that the language training corpora inevitably contains factual errors, and the model trained on this noisy data will learn and replicate those errors. And next, I will walk you through the post-training and hallucinations, how the evaluations reinforce the hallucinations. The core argument here is that most evaluations use dichotomous grading, which is a strict right or wrong grade scoring, which penalize the uncertainty. Under this system, abstaining of, for example, saying that I don't know, receives 0 point, and which is the same as a wrong answer. So a best guess, even if it's low confidence, has a chance of being correct and receiving full point. Therefore, a rational model optimized for these benchmarks will always guess rather than abstain, which encouraged hallucination-like behavior. And this paper analyzed several influential benchmarks and finds that they overwhelmingly used those right and wrongs grading, given no credit for abstention, like I don't know. And this creates a situation where a model that honestly report uncertainty will score lower than a model that always guess, even if they have similar underlying knowledge. And the authors argue that the that that simply create a new, better hallucination evaluation is not enough. The primary popular benchmark that dominate leaderboards must be changed to stop penalizing uncertainty. Otherwise, the incentive to guess will remain. So this paper proposed a solution to the problem of this right or wrong grading, reinforcing hallucination. And the key idea is to introduce explicitly confidence target into the evaluation instruction, like here shows in this like this system prompt. Like answer only if you are above T confident, since mistakes are penalized T over 1 minus T points, while the correct answers receive 1 point, and an answer of I don't know receives 0 points. And we can easily derive mathematically that so this is very simple derivation that we can get a model should only answer if its confidence P is greater than the target T with these settings. And this has two benefits. First, it removes ambiguity. The model knows the exact risk of guessing. This allows for fair comparison between models as they are all optimizing for the same explicit trade-off. And second, that instead of creating new benchmarks, this setting can be applied to existing inferential benchmarks, and this would change the and this also leads to the behavioral calibration, which means a model demonstrates its confidence through its action rather than just stating a number. And sorry. And finally is the discussion and limitations. This paper also acknowledged several limitations. First is that the theory assumed the model produced plausible strings and separates them into valid versus error. It doesn't really handle the like the random the random words with no logic or non-cynical output. But the authors argue that this is fine since modern models already rarely do this. And the second limitation is that the paper's model of error is binary. A response is either an error or it is not. This is a simplification for a very long and open-ended response like biography. A single falsehood makes the whole thing an error in this framework, which doesn't capture the nature of the mostly correct response with one mistake. And the third limitation is that the paper argues that even advanced technique like the retrieval augment generation (RAG) don't solve the core problem. RAG helps find facts, but if the retrieval information is ambiguous or inconclusive, or the two fails, the model still faces the choice guess or abstain, and those the right or wrong grading still push it to guess. And the fourth limitation is that the framework assumes that all necessary context is in the prompt. It cannot handle situations where the user's true intent is unclear. For example, if the user type in Apple, the model will not know if it is refers to the company Apple or refers to the fruit Apple. And The fifth limitation is that the proposed solution, like the correct, incorrect, and the I don't know scheme, is better than simply right and wrong grading, but it is still a simplification. It doesn't capture the different value of confidence or partial correctness. However, the authors argue that it is practical and objective step forward for the mainstream evaluation. And lastly, saying I don't know is a blunt way to express uncertainty. More often, human would saying something like, it is likely that, or I cannot be certain, but the paper focus on the simple I don't know case because it is a clear measurable action that can be easily incorporated into the scoring rule. And here is the conclusion. The paper the conclusion can be split into two parts. First, the paper illustrates why the hallucination originate after pre-training. The paper shows that these are a natural consequence of the statistical learning process from the binary classification or the cross-entropy loss. And it established a formal link between the rate of generative error, the hallucination, which is lower bounded by the error rate of a related binary classification, the IIV problem. And it means that if a concept is inherently hard to learn from the data, for example, the arbitrary facts that appears rarely, and any well-calibrated model trained to minimize standard loss function will inevitably produce errors, and hallucinations are not a mysterious flaw, but a predictable outcome of statistical learning. And second is that the paper state why the hallucination persists after post-training. So first, the hallucinations are reinforced by the evaluation ecosystem. The most influential benchmark uses the right or wrong scoring. And this scoring insensitizes the model to guess when uncertain, because a guess might earn points while abstaining, like just saying I don't know, earns 0. And this makes model optimized for leaderboard, behave like a student bluffing on an exam. And the last point is that the proposed solution is both social and technical. Instead of just creating new hallucination-specific benchmark, the paper argues that modify the scoring of existing popular benchmark by adding explicit penalty for incorrect answer. We can change the insensitive of the entire field and encourage the development of more trustworthy and less hallucinatory models. And that's all for the presentation, and thanks for your attention.